Okay. So in the last class, we discussed about t-test, right? Just one.
Excuse me, sir.
Yeah, let me know.
Sir, you have shared some files. So, two files are not accessible. Like a small data.csv file and full data, that both files are not accessible.
Not
Yes.
accessible.
That
Same
requires
here.
the access, sir, for the drive.
Since I could download it.
But we don't have access. Our IDs do not have access.
Okay, so don't do one thing. You do not have to worry about the big data, which is large data file that is available online. You can search about this bank data and you will get it. I'm right now for the purpose of the class, and let me share the small data. Okay, even that small data is just fun. So in the drive folder link that I have shared a drive folder link, right? Yesterday,
Yes.
where all the recordings are there. Have you received a drive folder link yesterday where all the
Yes, all recordings are there for
Yes.
till day 3.
Yes, in that folder under day 4, in that link under day 4 folder, session 2, you will find the small data. Download from there. Okay. So what I'm asking you to do is go to the link. Yeah, go to the link and then go to day 4, session 2, and there you will get that small data. You can download it from there because I could download it and I have already kept it here. So you can download it from there. So this link is what I have shared. It's not what Saptarshi has shared today, which I forwarded. Not that. The one that I shared yesterday. That one. Okay. So what we were discussing in yesterday's class was hypothesis testing, and we were discussing about t-test. Right. So this is what we were discussing. And what was there in t-test? I told you that that we are comparing either one group with a benchmark or I'm comparing two groups with each other. And what I am exactly comparing? I'm comparing the means. So means that the particular variable that I'm considering has to be continuous variable. For example, the score that you give to me, or let's say the average income or the average height of two groups. So that is, the variable has to be continuous. Then only this particular operation, the t-test or z-test, can be done. So can you give me an example of an application of this t-test where you are comparing the average of these two groups and you do not, so just by seeing at the average, you do not know whether one group is higher than other. Why? Because that has probably come up because of a sampling. You do not know whether they are actually away in the population also. For example, let's say I am trying to measure the average income of two uh, blocks or two villages. Okay. Now, one way of doing it is get all the data of all the villagers and then take an average. That means get the population level data and do an average. However, that might be difficult to do. So then what we do is we take a sample. Now let's say I took 30 data points from village 1 and 40 data points from village 2. And I am trying to compare whether just one minute. So I'm trying to compare whether these two groups are same or different, which one is higher, which one is lower, something like that. So to do that, I have to take this mean. Now let's say the first groups, 30 groups mean. So group 1, let's say, I got a mean of, let's say, around average income is, let's say, 5.6 lakhs per annum. And group 2, I got, let's say, 4.8 lakhs per annum. Can I say that village 1 will have a higher income than village 2?
With some confidence interval.
So that would also depend on the population of the village.
So let's say the population here it is 30, is the group size, here it is 40. And the population is, let's say, 1000. And this one is, let's say, 700. Now, so capital N are 700, small n is 30. Then, can I tell that whether these two groups have the same kind of income, or group 1 has higher income than group 2, or village 1 has higher income than village 2? See, alone this particular value does not tell me anything, because these might have come because of this sample. If I collect another 30 sample, I might get 4.3. Nobody can say that I will not get that. So alone these two values does not say anything. I have to find out what is the confidence interval from this sample. This is a sample mean. From that, I have to get a confidence interval of mu1 and mu2. Now, if these two confidence interval overlap very small, then I can say that this is higher than this, or this is different from this. But if these two confidence intervals overlaps a lot, then I cannot say this is the overlap area. Then I cannot say that they are different. Now that t-test and etc. basically is trying to measure how much is the overlap. It is exact by when we are doing two sample test, they are basically measuring how much is the overlap. And based on that, they are giving me the p-value. So this I have done, and in this case, the variable that I have considered is a continuous variable. For example, in this particular case, the variable was the income, which is a continuous variable. Now, there can be other examples of this particular problem. For example, let me ask somebody in this class. Keshav Rathi.
Yes, sir.
Keshav, where do you work?
Sir, currently I'm pursuing MBA.
Okay, then I will not ask you because but even then, let's say you are MBA. Can you tell me that? But can you tell me a real life application of this t-test in your?
So we were doing a research paper on that. We actually used this 2-sample t-test, and we tried to find out whether the growth percentage, or we can say the GDP growth of India, is equivalent to the GDP growth of Brazil. So we try to compare this using two sample t-test, and we can say that at one perspective, to know whether both the countries are growing at an equal pace with respect to the GDP percentage. So we use this, and it can be used in that sense also.
Okay, and what is your, you are taking yearly growth rate as the sample?
Yes, sir.
Okay. There can be better applications, but yes.
Right. There can be. We just wanted to try this out to understand that how this field actually works. So it was just a basic thing.
Okay, fair enough. If I ask you, Sandeep,
Yes, sir.
Sandeep, can you tell me an application of t-test in your, you work in auto insurance, right?
No, sir, I am with the Hero FinCorp again, model
I-
validation.
Can you repeat once more?
Hero FinCorp, model validation. We got a
So Hero FinCorp is what kind of organization? What is their job?
majorly to in lending. So we have two-wheeler loans and personal loans.
Okay, so auto loans.
Yes.
In auto loans, how can you tell me an application of this kind of a t-test in auto loans business? This particular method, can you apply anywhere, or you can see that an application is there? For example, do you run marketing campaigns?
Sir, yeah, I think, but yeah, we don't run marketing campaigns.
No,
But
you
I think,
means, I'm not saying you, I'm saying Hero FinCorp runs marketing
yes,
campaigns, right?
yes, definitely, yeah.
So how will they measure that whether this marketing campaign was successful?
So I think they would target that, after this marketing campaign, the approval rates or the sourcing rates should increase. So
Exactly. So if that is the case, let's say they have run the marketing campaign. Let me just give you the story that, let's say, yeah. So before marketing campaign, and after marketing campaign. So let's say before marketing campaign, they approached 81 people, and out of them, 7 were 1, 2, 3, 4, 5, 6, 7. 7 were ones, and rest were zeros. All rest were zeros. Nobody else have replied to this marketing campaign or bot. But after, so total, this thing was 81. And after marketing campaign, out of the whole sample that they approached, let's say they have approached total 97 people. Out of them, 10 were ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and rest was zeros. Now the question comes up is that whether the marketing campaign has worked or not. So how will I answer that? Idea is that, okay, it is basically 7 by 81. That is my mean. And in this case, it is 97 by, sorry, 10 by 97. But this is a sample mean. You take another sample, the values will change. So I have to compare this mean with this mean in some way or other. How do I compare? I also compare that what is the confidence interval. For confidence interval, I have to find out the S also. So if it's a 1, 1, 0 kind of thing, I do not know whether you know that or not. The S will be exactly this. If you calculate your standard deviation on your own. I'm just giving the formula because I know this. For proportions case, this kind of a formula comes up. So you know now the standard deviation, the mean, the standard deviation, you check the overlap. If it is overlapping a lot, then your marketing campaign did not work. That means these two groups are more or less same. There is no change in the average conversion probability. But if it does not overlap, let's say if this is like this, which is pre and this is post, if it does not overlap, then you can say that, okay, it worked pretty well. So these are some of the applications. You can apply it in a let's say process industry, also in a manufacturing industry. You wanted to see that you have two lines in which you are making certain products. You want to check that whether the average performance of these two lines are more or less same or not. You cannot measure the performance of all the products that is coming up, but you can measure a sample. Now that sample, two samples collected from two different I would say lines of production, you have to compare that. And when you compare that, you basically know that whether they are same or not. So this kind of questions, this kind of problems, when two groups are comparing or you're comparing yourself with a benchmark, in this kind of situations, this t-test comes into handy. But however, whatever be the case, the variable, the y variable, the variable that you are measuring, the mean that you are calculating, has to be a categorical variable. Now, we can also try to find out something called ANOVA. What is ANOVA? ANOVA actually looks into situations when there are a y variable which is continuous, same like the previous one, and x variable is categorical. X is categorical. But you see, in case of t-test, the number of categories has to be smaller than equal to 2. Why? Because it can be one sample test, that means only one category is there, or two sample tests, two categories are there. However, ANOVA is used for greater than equal to 2 categories. Let me give an explanation what I'm trying to say. Let's say I am trying to measure the malnutrition level of women in 3 or 4 states, let's say UP, Bihar, Jharkhand, and West Bengal. I'm trying to measure the malnutrition level of women. Now, can I take data from all the women in these 4 states? Probably not. So then what will I do? I take sample from the 4 states. Let's say each of the state I collected a sample of 2,000 women in each state. Now I got 4 different means. Now if I want to compare that whether these means are same or different, how many t-tests do I have to do? I have to do 4C2 number of t-tests. That means I have to first compare West Bengal with Jharkhand, then West Bengal with Bihar, then West Bengal with UP, then Jharkhand with UP, Jharkhand with Bihar, and then Bihar with UP. There are 6 different comparisons I have to do to test whether they are same or not. Now, if I have to do the same activity for all the states now in India, then you imagine the number of t-tests becomes very huge. And this is difficult to actually, it will increase non-linearly and it is difficult to achieve. In that kind of a situation, a methodology called ANOVA comes in. What is ANOVA? It is also told as analysis AN of O variance. So it basically deals with the variance between the data sets, between the groups to calculate, to answer this question. So what is the null hypothesis that we try to answer? Let's say if there are three groups, mu1, mu2 and mu3, there are three groups, let's say group 1, group 2, group 3. The assumption is that three means are same. An alternative hypothesis is at least one is different. We are trying to test this, that at least one of these three groups are different. Now, how do I test this thing? So here we try to check something. So let's say this particular assumption is dependent on some common sense, and let me just draw those common senses in front of you. Let's say there are two groups. Both has a distribution. Group 1 looks like this, the distribution, and this is the mean. Group 2 looks like this, and this is the mean. This is situation 1. This is group 1. This is group 2. On the other hand, I am also giving you situation 2. Well, group 1 falls at the same location, and group 2 is here. If I ask you, out of these two situations, in which situation the groups are, you are more confident that the groups are not same or not equal. The group means are not equal. What will you answer? Out of these two situations, in which situation you are more confident that the population means are not same? Tell me.
Situation 2.
Situation 2. Why are you choosing situation 2?
So it means
The means are away, more away. So in other words, the further away the sample means are, the higher is the distance from population. I'm just giving words to whatever you are thinking. You agree with this line? The higher, the further away the sample means are, the higher is the distance in the population. You have to say yes, no, I agree, disagree. You have to say something.
Yes.
Okay. Now, let me give you another situation of two groups, two samples. Let me put another picture. So this is a straight line. So as usual, this is situation 1. And this is situation 2. And this is the first case. This is group 1, this is group 2, and this is the second case. Group 1, group 2. Now you tell me, see, the means are exactly equidistant in both the cases. In both the cases, here is the distance of means, here is the same distance of means. Now tell me, from this picture, if this group 1 and group 2 are basically the sample distributions, what will you talk about the population? In which situation the population means are more distant as per you?
Sorry, the population mean are what?
More distant from each other, means they are away from each other.
Okay, so situation 1, because I mean the population is spread over a long distance from the average mean, and then situation 2, if we see the most of the population is closer to mean.
Okay, so then in which case the distance is higher?
The first one.
In the first one, the population, distance of the population means from each other, means population.
Yeah, distance of the means is same for both.
So understand what I'm saying. These are sample means. The picture that you are seeing, group 1 and group 2 are of sample. Okay, the sample distribution. That means you have taken, let's say, 1,000 women from group 1, let's say West Bengal, and 1,000 women from let's say Jharkhand, and then you put them in a distribution basically. So let's say this is in the x-axis is the malnutrition score. Okay, and let's say this is West Bengal. The higher it is, the higher the. So this is the average malnutrition of West Bengal. This is the average malnutrition of Jharkhand. Let's assume. And these are the distributions. Various figures are coming up here for Jharkhand, and also here for West Bengal. Now these are all sample observations. I'm asking from this picture, tell me that similar things are happening here. This is for Jharkhand and this is for West Bengal. My question is, out of situation 1 versus situation 2, in which case you can say that the population malnutrition in these two states are different from each other? In which case you can say very.
Again, situation 2.
Yeah, 2.
Why you can say situation 2? Why not situation 1?
Overlap, due to overlap.
Due to overlap. This basic thing is overlap. And when does this overlap come down? When does overlap does not happen? What do you see in these two things?
Standard deviation is less.
When the standard deviation within the group is smaller. So the lower the standard deviation within the group, the higher is the distance. In population means. We use this thing in t-test, but we do not use this one. This one we use only in the second idea. Given this thing, what I'm trying to say, that I will reject the null hypothesis. So I am trying to say that I will reject the null hypothesis as long as I get high between group distance and low within group distance, right? If this happens, then I can say that population means are distant. That means I will reject this null hypothesis. The new one is going to mu2 is mu 3. I will reject it. In other words, I will say that high between group distance and high 1 divided by within group distance. So low within group means high one by this, right? So in other words, I can say high between group distance divided by within group distance. As long as this ratio goes up, as long as this ratio is going up, I have higher probability of rejecting the null hypothesis. So this is the crux of ANOVA. This is the crux that we are going to use in ANOVA. So how to measure this between group distance? First of all, within group is very easy. How to measure the between group distance? That means how distant one group is from the other group. The measurement of that is summation of each group's mean with the overall mean. So let's say if xi dash is the first group's ith group's mean, then that minus the overall, all the observations together, all the 4,000 observations from 4 states together, their mean, square of that. This is basically, this particular thing measures how, if it is the mean of the all the 4,000, and if this is the mean of West Bengal, if this is the mean of Uttar Pradesh, this is the mean of let's say Bihar, and this is the mean of Jharkhand, then this particular thing is basically measuring this distance, how these guys are distant from the overall mean. How these observations are distant from the overall mean. This particular thing it is measuring. So summation of these values into the so divided by the number of groups minus 1. So if there is I is equal to 1 to k, then k minus 1. So average distance. Similarly, if I try to find out the within group means inside the group distance. So that is basically ni minus 1 si square. So si square is the standard deviation of each of the group, each of the sample. Ni minus 1 is the and then I do a weighted average. So basically summation of ni minus 1. So it can also be written as something like this, that summation of ni minus 1 si square divided by in total means all the n's together, if 4,000 minus number of groups, which is 4. So if you do this, you can get this. Now, why this formula? Why this particular thing that I'm doing? I'm basically taking a weighted average of the groups standard deviation. So if I have to measure this group standard deviation and this group standard deviation, I'm taking a weighted average of these two groups standard deviation. And what is the weightage? The weightage is number of observations minus 1, because that the same degrees of freedom thing comes into the picture. That's how I'm measuring this within group distance. And my F statistic is this ratio of between group versus within group. So as long as F increases, if F is higher than a cutoff F that we decide, then reject null hypothesis. F and P are inversely related. If F increases, there is a P, that means probability that you will do a mistake by rejecting the null hypothesis, that drops. So as long as F is smaller than the cutoff, which is alpha, 0.05 or whatever you decide, reject null hypothesis. Now these maths happen. This particular maths happen at the back end of ANOVA. We are trying to categorize that whether multiple groups are having the same kind of means or not. ANOVA's usage is pretty low, but this is something still it should be known, because in some of the fields, for example, in biology and etc., this particular methodology is used a lot. Not all of it, not in all areas it is used, but in some of the areas, like in process management, in manufacturing industry, in biochemistry or biotechnology kind of industry, this particular method is used. But whatever this method is doing, even regression can do that. We will come to that quickly. So if I want to just quickly show the implications of that, implementation of this, let me open the Jupyter notebook. I've shared a Jupyter notebook called Chi-Square and ANOVA to you guys. So I would request you to open that.
I have a question, Amin. So,
Yes, please.
what is F cutoff?
This F cutoff is decided like this.
Yeah.
If distribution looks like T distribution I have drawn yesterday, and based on that we use a T cutoff. If distribution looks like this, it starts from 0. It's a distance, right? It starts from 0, goes up to infinite, and it looks like this kind of a curve. Here it starts from 0, but it ultimately reaches infinite.
Okay.
So F cutoff, if you choose alpha is equal to 0.05, then this area is alpha 0.05, corresponding this value, above which this. So the F cutoff is basically F inverse of 1 minus alpha. So you find out that value of F for which above that particular value there is probability of something happening is 5%. Something means what? Something means this ratio, this between group by within group ratio. This ratio, the probability of happening this ratio over and above this particular value is 5%. We find out that value. Now, how this F values were created? People have, historically, people have created multiple such tables and created these F values for each of the tables, and found out that how many tables are higher than this.
Sorry, I lost the track, sir. I mean, didn't quite understood what you've said. So, okay, this is a graph you've shown. So that goes till infinity.
Yes,
Then,
this graph is the F distributions graph.
Okay.
Like there is a T distribution, there is a F distribution graph.
Okay.
And what this distribution talks about, it is basically F distribution measures ratio of two variances. That's why it is ANOVA. It actually ratio of two variances. That's what it generally plots. Now this curve starts from variance is a square term, right? Variance is some error square. So if it is a square term and it is a ratio between two square terms, what is the lowest possible value of this? If the numerator is 0, the error is 0, then the f value becomes 0. So the lowest possible value of f, which is a ratio of two variances, is 0. And if the denominator becomes 0, then f becomes infinite. So the highest possible value of f is infinite. And f varies between 0 and infinite in this kind of a way. Now, I will find out such a cutoff of f. Higher than that, there will be only 0.05 number of cases if I have a 95% confidence interval. So only 5% of cases will happen higher than that. So I am telling you right now, so how this F curve is created? How does this curve look like this? Let's say I have two populations, okay? I have two populations, population 1 and population 2. They are identical population. Exactly identical, okay? Here also 100 people are there, exactly same 100 people are also there. Now I take a sample of this 100 people and create one S1 square. I take another, sorry, out of this 100 people, I take a sample of S1. Oh, sorry. Out of this 100 people, I take a sample of, let's say, 36 people. And out of this 100 people, I take a sample of 36 people again. Same. I can get so these 36 people and these 36 people will be different 36 people, right? Although their population is same, if I take two different samples, the persons will be different.
Yes.
I will get different x1 bar, different s1 square, different x2 bar, and different x2 square from here.
Yes.
I will get from this using the formula that I've written here. I can calculate one f. The formula that I have written here, based on this, I can calculate a f for this particular case.
Yes.
Now they have done this f and saw that the f falls here. Like that, if I keep on doing this f, this is activity number 1. Activity number 2, I again do the same kind of activity, get another f. Activity number 3, I get another f. Activity number 4, I get another f. Activity number infinite, I get infinite such f's. Such infinite such f's, if I plot in this curve, it will look like this. The histogram of them will look like this. With the population,
the y-axis?
Y-axis is frequency, x-axis is the F scores. Frequency of F scores, right? That means, let's say some F is falling in this region, some F is falling in this region. It's a bar chart. How many Fs are falling in this region? How many Fs are falling in this region? And so on. If this bar chart you join with a spline, that black line comes up.
Okay.
Okay, that's how a distribution gets created. That's how. Now this distribution, you see, this is being created from initially I had a same sample, sorry, same population. This F curve is coming from same population.
Yes.
Now, if that is the case, and if I reject one F here, let's say I got a F here, and I say that because the F is very high, I am rejecting the null hypothesis that the two populations are same. I am doing a mistake, right?
Yes.
What is the percentage of doing that mistake? This shaded area. This shaded area.
Okay.
So if I take a rule now, based on these curves that I have made, if I now make a rule that anything, any F value falling in this region, I reject the null hypothesis, then I will do a mistake with only 5% probability and I will be correct 95% times.
So you're saying that this area says that if we reject the null hypothesis,
I will be doing a mistake. I will be doing an error. We call it type 1 error. I will be doing a type 1 error 5% with a probability of 5%. So if I reject the null hypothesis, that what was the null hypothesis? That the populations have same mean. So
yeah.
if the populations have same mean, then 95% times the F will be here. And only 5% times F will be here. So now if I make a rule that whenever the F is here, I reject this line, I reject this particular statement, then I will be doing a mistake, doing a wrong, only 5% times. Right? You understand what I'm saying? Because if this is true, only 5% times I will get a F here. Most of the Fs I will get here only. From this point to this point. 0 and F cutoff.
So, sorry, I mean, still trying to absorb, but then I understood what you're saying, what you've said, but then this 95% cases, F is small. It means the null hypothesis stands good. So population have same mean. So 95%, we are saying that, okay, if left-hand side graph, we are saying that, okay, we are retain, I mean,
No.
we're not rejecting null hypothesis.
So understand once. So I have created this graph using this thing. I started with two populations,
Yeah.
Same population. I created this graph.
Yes.
This
So
graph only says that when two population means are same, two or more, let's say, I don't care, but I can, if I can do it for 2, I can increase the number of population, right? And do the same activity. If 2 or more populations are same, then 95% of times the F score will fall between these two values. The F score. This is frequency. This is the F score. So this area under the curve is 95%. So it is saying that 95% of the times, all the Fs that you observe out of this population, 95% will fall here and only 5% will fall here. This much it is saying, telling to me. And when population means are same, this is what you observe. This is what you should have observed if you have kept on doing the activity.
And the cutoff is fixed, you're saying that's 5%.
That 5% is fixed because, yeah, means you can choose 5% to 1%, then the cutoff will be here. If you want a 1% thing, the cutoff will be here. You change the cutoff.
And how can we choose this 5 and 1%?
Okay, so that I will come to that. Let's just assume thumb rule, I am choosing 5%. I will come to that. Okay.
So,
Just
but
one.
this will only be the case when the two populations are identical.
Two or more population,
Okay.
populations are identical, then this situation happens. Now let's say I do not know whether the populations are same or not. I took group 1, group 2, group 3, the one that I was talking about in West Bengal, Bihar and Jharkhand and Odisha. 4 groups I calculated. From there I took a sample and I calculated a F statistic. This is my calculated F. Now I have calculated it. And you have only given me this graph. You have not given me anything. You have given me this graph and I have calculated it. Now I see this F value falls here. This F value is here. This one is the F value that I have calculated. Now, if I reject the null hypothesis, if I say that these groups are not same, these groups are different, these groups are not same. If I say this, then what is the probability that I am doing a mistake? The probability of I am doing a mistake is basically the probability of getting a F score here, even when this is true. Probability that getting a high F score with same means is also probability a high F score rejecting null and doing a mistake by doing that. Because rejecting null and doing a mistake means null is correct. Null is correct means same mean.
Yes.
Right? So that means if I reject a null hypothesis here, the probability that I'm doing the mistake is less than 5%, less than equal to 5%. Basically exactly this area. This is the mistake that I'm doing.
Okay. Okay. Yeah. Thanks. I'm sorted.
Okay.
Yeah.
So if that, so this curve came from this kind of an activity, which historically statisticians have done. But once this curve is given, nobody will give you this, ask you to create the curve. The curve is given to you. Once the curve is given to you, you have to just calculate what is your F score and corresponding P score. P score is this probability, this shaded, black shaded area that I created just now. If the P score is smaller than 5%, or your F score is higher than the F cutoff value, any one of them, generally we go with the P score only. Then I reject the null hypothesis, otherwise I do. So this is what a t-test is. Sorry, a F-test is where multiple groups are there. So let me show you an implication. The application is very easy. So here you see in the ANOVA, I read a data set here, and just see this picture. So you will see the lines. Just see this picture. There are 4 groups, A, B, C, D. 4 kind of treatments that has been given to certain patients, let's say. And do you know what is a box plot? Has it been taught to you? Did Gaurav teach
Yes.
box?
Yes.
Box plot is taught, right? So you see these values are the median values. The median is pretty high here. The median is low here, and its median is almost in the middle here. However, there are quite a lot of overlap. For example, this one and this one has some overlap. This one and this A and C has quite a bit of overlap. D is a little bit away. So in visually, you can say that, okay, sir, these are more or less different. I can see that. But we have to also test it. And sometimes visual and actual value is not exactly same. Sometimes you are not sure. If there is a marginal level of overlap, you are not sure exactly whether you can say that these groups are same or not. So what I do is very easy. I write stats dot. So in the stats package, which comes under spicy. Spicy we were using yesterday also for t-test. So import spicy.stats as stats. Under the stats package, there is F one way. That is one way ANOVA. And I have chosen the 4 columns. DF datasets, the dataset that I've just read. A column, B column, C column, and D column. 4 columns are there. You calculate the F value and P value from that. That's what I asked them. And then asked them to print it. So when they printed it, I got, oh, sorry. Run this first. When I printed it, I got F value as 17.49 and P value is 2.64 into 10 to the power minus 5. If you see this figure, this is 2.64 into 10 to the power minus 5. That means much lower than 0.05, which means that these 4 groups are different from each other. We can also do it using ANOVA like this. This gives you a better look at the calculations. You see, this was the sum of squares, which was between the groups. And there were 4 groups. That's why divided by k minus 1. If you remember, that's how I wrote the formula. And this is the mean between group sum of square. Similarly, this is the mean within group sum of square. The same formula. There were 16. Why it is coming 16? There is, I think, 20 data points and 20 minus 4. 20 minus 4 number of groups are there. That is the 16 which comes into the denominator in the in this formula. In this formula, it's coming in the denominator. You see nt minus k, and the numerator is n minus 1 is ni minus 1 si square summation. That they have calculated to be 918. You can do it on your hand also once you get the data. And then this is the ratio. And then 1003 by 57, which is coming around 17.5, that is your F score. Corresponding F score they put in the graph that I have just shown and found out what is the p value. As long as that p value is more than 0.05, you can say that these things are different. Your groups are different. So ANOVA has its application in certain places. For example, oftentimes later you will find out that we are trying to run a regression, and we try to choose automatically which categorical variable to choose. In such kind of a situation, ANOVA will come very handy because that will give you that out of many categorical variables that you have, which one to take and which one not to take. Then you run a predictive model. So this is hypothesis testing. It is just telling you that these groups are different. It has application in this phase. For example, if I can tell that the 4 groups are different in terms of malnutrition, these 4 states are different, then I will further probe why they are different. If I can say that they are not different, then I will stop probing. So to do any kind of predictive analytics, any kind of further probing inside this thing, this ANOVA plays a very important role.
Apologies, sir, but then what was that? I mean, can you scroll down? This seed treatment and residual, I mean, that's something which I again didn't understand.
So seed treatments are basically so there are 4 different kinds of treatments, A, B, C, D. So that particular variable in the data set has been used as the treatments. C for category. Okay, so convert these treatments as category and then you use that in the model. So let me show you the data set. Yeah, just 1 minute. Show you the data set.
Okay.
DF, right? Yeah. So this is the data set that I got.
Okay, 4 data sets we have.
5 observations and 4 groups. 25, 30, 28, 36, 29 was first, whoever got treatment A, their score. And 45, 55, 29, 56, 40 was whatever, whoever got group B. So when I do DF is equal to DF melt, I basically convert it to their melted version. That means this one is a we call it white, and then we are converting it to its melted version. So let me just show you. Just 1 minute.
Sorry, this melting I didn't get.
Just 1 minute. Let me show you what is DF melt. Melted version of the data is nothing but this. This is called melted version. Index, then instead of writing it like that, we write it all the treatments in one column and all the values in another column.
So basically a transpose thing.
Yeah, not exactly transpose. It converts one column at a row, one row at a column. So one column and then another column in another column at the bottom of one column. It appends one column at the bottom of another column.
Okay.
Okay. So this is called long version. This is also called long. So just search long and wide. What are the two types of data set?
Long and
Wide. Long and wide. WID. So these are two ways of reading the data set. Doesn't matter. But this is the version that we have to use when I am doing ANOVA. So all the treatments, there will be treatments in one column and the value in another column. Okay, now with this DF melt, they are running, see, value becomes my Y variable. Tilde means basically it's a functional form. And then this is my X variable. If I had more number of X variables by any chance, if I had, let's say, treatment also and then gender also, I would have written this class gender, something like that. We'll do that in regression. As I come to regression, you will see what is the meaning of this. So I can add more number of categorical variables, and the result will come for those categorical variables as well.
so this is a text or what? I mean what we have in quotes, value tilde C treatments.
So value tilde C treatments is trying to say that, see, in this data set, I have two columns. The value column is my Y variable.
Yes.
And treatments column is my X variable. So when we run a model, it's a very common way of writing a model, which is Y tilde X if there is only one X variable. Or if there are more than one X variables, then Y tilde X1 plus X2 plus X3. This is a very common way of saying that Y is a function of X1, X2, X3, linear function.
Yes.
So this represents this.
Okay, yeah.
So I am trying to say that run an ANOVA where value is your Y variable and C, categorized version of treatments, as your X variable.
So this is treated as a command, or I mean this would be
It's a
just
command,
a
it's a
text?
syntax. It's a syntax.
Okay, it's a command. You're saying syntax.
Yes. So if I had some other variable here, instead of treatment, let's say I had gender, then I would have written gender here. Let's say I want to see how the value of whatever, let's say this value is the income of people in our organization. How the gender impacts income, or whether gender-wise the wages are different or not. So I would have written that particular variable. So the Y, whatever is the name of the Y variable, that will come here. Whatever is the name of the X variable, that will come here. The overall syntax is this.
So do we have treatments also somewhere in the data set? We only
Yes, just one. Yes, we have treatments, right? This is the treatments. The data set, the column name is treatments.
Okay, fine. Sorry. Yes, we have. And what do you mean by C here?
C is change it to category. By chance, if difference was as a numeric data, it would have also converted it to a categorical data and then did the analysis.
Okay, so since it's A, B, C, so we don't need C, but then for the
We don't need
syntax-
C exactly. They have just written it.
Okay. Okay, so it's saying that value is a function of treatments.
Yes, value is a function of treatments. So C value as a function of treatments, break the data set based on treatments, and then you do the calculation.
Okay. And this PR is what P value?
This is the P value. Probability that you will get a F higher than this calculated F. Probability that a F can be obtained higher than the calculated F. The calculated
okay.
F is a black line. Probability that any F can be observed higher than this.
Okay, and what? So first row is clear. It's the final the final thing which we want to see out of this ANOVA. But then what is residual?
Residual is the second row. Basically, this is, you can say this is the within group distances. Now, why that is termed as residual? This is a question that you can ask. That's how you have taught me between group and within group. If somebody would have written that, I would have not any problem. But with this much, I can understand that this is within group. Instead of within group, they have written the group names between. But sorry, this is between group. Within group 5, they have left it as residual. Let me explain you this much. This one. Let's say, okay, this can be explained in this way. Can I show you an Excel file? Just 1 minute. Be with me, huh? Just 1 minute. Be with me. Quickly show you something. So A, B, C. Let's say there are 3 groups, huh? And these values are 2, 3, 4, 5, 4, 5, 6, 7, 8, 3, and 4, 2, 6, 7, 5. Some 3 groups, okay. So what is the total variance of this group? The total variance of this group is variance of this sample. This is the total variance of the group. I'm writing it here. Now, what is the variance of each of these group separately? So variance of each of these groups separately is this. Then if I drag out this one. So this is the variance of each of this group. This is the mean of this group, which is average of this 5 numbers. So mean of overall is the overall mean, average of all the 15 numbers, and the within group distance, sorry, between group distance, between group plus what is the distance between 3.6 and 4.73. So this minus this is square, and before I drag, I will put a F4. This is the overall distance. Okay. So what I'm trying to say here is that total between group distance is then the sum of these three numbers. Just 1 minute, huh? Just be with me for 1 minute. This is total distance. Total sum of square. So this into number of observations is 15 minus 1. This into 14. This is the total sum of square. Total sum of square is this multiplied by 14. Between sum of square. This value is the between sum of square. Sum of these three values is the between sum of square. And sum of these three values is the within sum of square, which is basically 4 into summation of these three values. Okay, now this is 14. Just be with me for 1 minute. See, what I did the calculation. So these were my 5 groups. 3 groups, sorry. 3 groups, each had an observation of 5. This was my total variance of these 15 observations. What I did here is instead of 15 observations, I multiplied these 15 observations with 14. By 14, it is 15 minus 1. What do I get? I get total sum of square. Let me just write down what is the calculation of this 46.93. This 46.93 is called total sum of square, which is 14 into variance. Remember, of the variance of all the 15 people. That means NT, total number of observations into minus 1, multiplied by summation of individual observations of all the groups. Let's say group number J is equal to 1 to 3, and in each group there is 5 observations. I is equal to 1 to 5 xij divided by x double bar square divided by nt minus 1. This is the formula of the variance. Each observation, why I wrote 2 summation, that means I varied from 1 to 3, 3 groups are there, and then J varies from 1 to 5. That means there will be 15 such cases here will come, minus the overall mean of those 15 cases, then the square of that. So this becomes something like this. I is equal to 1 to 3, J is equal to 1 to 5, xij minus x double bar square. Who asked me? Who asked this question to me?
Yeah.
What's your name?
My name is Gaurav, sir.
Gaurav. Okay, so Gaurav, this is the total sum of square. That is the calculation that I have just shown. So
Okay.
this is a measurement of the total error in the data, total variance in the data. This is a total variance in the data. Now you see what I did next. So this calculation, and after the calculation, it came up to be, this value came up to be, I think 46 or something like that, right? Let's find out. The value was how much? 46.93. So 46.93. This is the value I got. That's the total sum of square. Now next what I did, you check these things. I calculated the mean. This is the average of these 5 numbers. Okay. I calculated the mean. So that means these are the sample means, X bars. These are the sample means. I calculated 3 sample means. And I also calculated the overall mean, the mean of all these 15 numbers, which is the X double bar that I was writing there. X double bar that I was writing there. Then what I calculated the distance of this 3.6 and 4.73, square of that. 5.8 and 4.73, square of that. 4.8 and 4.73, square of that. Then I added this between groups and multiplied by the number of observations in each group, 5. What I did is basically calculated the numerator of this formula. The numerator of this formula, there was a small mistake in this formula. It would have been into Ni. So I calculated the numerator of this formula. What I did, what I have calculated is this 30.13. In this particular case, it is 30.13. In my case, it is 12.13.
What is BSS?
BSS is between sum of squares
Between
or between group errors. How? What does that mean? That how the sample means are distant from the overall mean. The measure of that between group error is what I measured. So that came 12.133. Similarly, I can also measure this part, this part, which is Ni minus 1 Si square. So Si square is what? The variance, 1.3, 3.7, 3.7. Ni minus 1 for each of them, it is 4 because the observations are 5. So I added it up and multiplied by 4. What I got is 34.88, which is called within sum of squares or within group distances. Now this between sum of square and between sum of square and within sum of square totals to be 46.93, which is exactly same as TSS. So it can be calculated in any case. So what I tried to say by showing this demonstration is that the total variance, not variability, I will not say variance, total variability in the data, which is measured by total sum of squares, is equal to distance between the groups, which is BSS, plus distance within the group, which is WSS. We can also say in another line that TSS is equal to error that is explained by the group or variance that is explained by the group, which is BSS. So the groupings are explaining why they are different from each other. I am saying that the malnutrition of one group is different from malnutrition of another group Because one group is from West Bengal and another group is from Bihar. So that the name of the state is explaining their difference. That is between SS. But within SS is what the groupings cannot explain. Within SS is the variance within the people who are from West Bengal or within the people who are from Bihar. So why two persons from West Bengal are different in their malnutrition level? The state's name cannot explain that. That is the residual. So it's another term that we use. That this is the part that my groupings cannot explain yet. I have to use some other way to explain this. That's why they are also called residuals. Could you understand what I told?
Yes. Yes, I mean, maybe there's some time required to absorb all this, but then gist is what we've understood.
So
what
let's.
residual actually mean.
So did you understand this part?
Yes.
So I can prove it mathematically also. I can prove it mathematically. This formulas leads to this formula. But I'm not doing that. I'm just showing you. That's why in this Excel form, you can check it
Yes.
at a later point of time. You can check it on your own.
Yeah, this is very helpful. I mean, if you can also save this for us.
I will save this one.
And because
so this is how I calculated WSS or within group distance, whatever you say. This is BSS or between group distance.
Between group distance.
And then the degrees of freedom in this case was, if you remember, the first case was number of groups minus 1. So here, degrees of freedom was number of groups minus 1 is 3 minus 1, 2. And here it is NT minus K, that means total number of observations. Total number of observations 15 minus K, 30, 3, 12. So that gives my F score to be this value within divided by this value. That comes in my numerator. This comes in my numerator. Then divided by this comes in my denominator. This F statistics is coming also something around 17, which is pretty high. So corresponding the p value is f dist. If you can solve here, f dist this comma 2 degrees of freedom we have to write. First degrees of freedom, the second degrees of freedom, and f statistics is cumulative is 2. Yes. So 1 minus that is my p value. So 0.0003, very low. So these three groups are different. That's what my particular thing is saying. And I can say that because the mean set you see at one is 3.6, another is 5.8, another is 4.8. So they are more or less different. They're not same. And the p-value is also saying the same story. So that is the calculation what we are doing. I'm saving the Excel. I'm also saving this particular table. You can check on your own.
So basically, we are not much concerned about this residual thing. So what we want is in the first.
Yes. Yes. We are more so that see the understanding is the higher the residual is, the lower is the overall F statistic. If this value becomes higher, the F statistics will automatically come down. Because this 17.49 is a ratio of 1003.65 divided by 57.375. This ratio is that 17.4928. So if 57.375 goes up, the F statistics will automatically come down, and F comes down means they are not distant from each other. They are same. Fair enough?
Yes.
Okay, so next I am going to another topic which is called chi-square analysis. This one is easy, much easier than probably ANOVA. One of the easiest of the hypothesis testing. So what we are doing here in case of chi-square analysis is that till now my y variable was continuous and x variable was categorical, and I was just testing whether they are same or not, the means are same or not. In chi-square analysis, both x and y are categorical. For example, let's say I'm trying to measure that whether there has been allegation that in a particular organization there is gender bias in terms of which department will have what kind of uh, people, what gender of employees. Let's say there is a finance, there is production, there is marketing, and there is HR. So we take a sample of people out of that organization and we see that what they are fitting. So let's say I got 4 and 2, or let's say a little bit more, 14 and 12, and let's say I get 35 and let's say 8, and let's say I get 15 and 10, and I also get say 8 and 7. This is my observation. This is what I observe from the sample. So total there are 26 from products, 43 here, 25 here, and 15 here. So it adds up to be 51 and 94, 104, 109. And 15 and 10, 25, 37. If I get this is 72. Just check whether the values are correct or not. So this is what I observed. Out of the 109 sample, this is what I have observed. Now I want to test my null hypothesis is in this particular condition that there is no relationship between the gender of the person and between the gender and the department. An alternative is there is some relationship. So what kind of relationship we will further probe if this comes to be there is some relationship. Now I will ask you that if I blindly choose somebody from this group, what is the probability that person will be a female? William, can you answer that? If I blindly choose somebody from this group, what is the probability that the person will be a female? Okay, anybody?
37C109.
37C probability I'm asking. Probability has to be between 0 and 1.
37 divided by.
37 divided by 1. Yes. 37.
Yes.
What is the probability that that person will be from production?
Forty-three by 1.
Now, if female, being female and being from production are independent of each other, being female and being production are independent of each other, what is the probability that somebody will be from female, somebody will be female and from production?
P production into PF.
So what will be the value?
43 into 37 by 109 square.
This will be the value. So then out of 109 people, how many should I expect to be in this group? This probability into 109. Are you with me? So how much is that value? This by this cancels out. 37 into 43 divided by 109. You see, I am talking about this particular this thing. So I have taken this 37, which is the row total, this is the column total, and this is the grand total. So you can check for each of this cell, it will be row total into column total divided by the grand total. So if I can calculate that, I can calculate for each of the cells what should be the expected numbers. I should be able to calculate that. For each of these cells, male and female, and finance, production, marketing, and HR. For each of these cells, I can say that this is row total into column total by grand total. This is row total into column total by grand total. Each of them will have different row total, column total. And I can calculate these values. What are these values? These are the expected values, assuming gender and department are independent. This is the expected value that I expect to see, and the red box is what I actually see. Now, if the blue box and the red box are similar, then what will be my inference? If the numbers in the red box and the numbers in the blue box are similar,
Independent.
they're independent. If they are not similar, what will be my inference?
Related.
They are related. So I will reject my null hypothesis if the red box and blue box are distant from each other. And how to measure that distance? The measurement of that distance comes from chi-square. So chi-square, the formula of chi-square is observed values minus expected values square divided by expected value, while I is equal to 1 to the number of cells. So each cell, I calculate the, what is the lowest value of chi-square? If the tables are absolutely same, what will be the value of chi-square? Come again?
Zero.
What will be the maximum possible value of the chi-square?
Infinity.
Finite. Because if any of the cell, if any particular cell's expected value is 0, then chi-square becomes infinite. So, so chi-square also looks like F curve, a little bit more steep. It also has a cutoff chi-square in the same formula. If your calculated chi-square value is higher than this cutoff, or your p-value is lower than 0.05, p is low, or or chi-square calculated is higher than chi-square cutoff, any one of them, reject your null hypothesis. Used very much to check whether two categorical variables are related. Two continuous variables are related or not are checked using correlation. We will talk about that. I will not cover that today. Next week I will cover that. But two continuous variables relationship between each other is checked using correlation. One categorical and one continuous variables relationship is checked using t-test or f-test, depending on how many categories are there. And two categorical variables relationship is checked using chi-square test. So how to do that? Let me just implement it. So this you can calculate on your own. If you have given this particular table, this table you can calculate on your own. If you can calculate this table, then this distance calculation is not anything impossible. You can again do it on your own in the hand itself. I can quickly do it in Excel if you want, and then you can calculate here. So let me do it in Excel once, and then I will do it in this thing. So let's say
I have a small confusion. I mean, can you go to that second last slide? Just a very small one. Sorry for that. So what is this N, F, and prod?
MF is male and female. Prod is production department. Let's say
No. This N. I mean, in the calculation, if you see, yeah, please come down. The second last row. Yeah, N. Yeah. Just underneath this. So you've written F and prod. In bracket outside, you've written N.
that's one. N means number of observations that you expect.
Okay, number of observations.
What is the probability of an event? The probability of an event is what? Number of times the event occurs by the total number of observations, right? That N.
Okay.
So then if this is P, then N of the number of persons that you expect to be like this, is this probability into this total number of persons?
Yes.
This is equal to F of comma prod multiplied by the total number of persons.
Yes.
That's what I did here.
Okay. Yep. Thanks.
So let me quickly do this thing in Excel once. Then you will understand it, and then we will do it in Python. Very quickly. So let's say some values I put. So finance, production, marketing, HR, and values were 35, 8, 14, 35, 8, 10, 8, 7, 15, 10, 8, 7. So this was basically sum of these two values. This was sum of these two values. This was my observed table. Okay, fair enough. This was my observed table. I copy this table, paste it here to create my expected table. What was expected table? Each of my this thing will be this total into this total divided by the grand total. Grand total I will make F4, and here when I drag, I will keep the J intact. So here I will this, and here I will take the 6 intact. Just 1 minute.
So shouldn't we take J6 instead of J11 in the
Yes.
formula?
Sorry, I was checking. Yes. Sorry. Yeah. And then if I drag it up and drag it down, I get the same figures. Okay. So just check. This one is row total into column total by grand total. Each of them will be like that. Yeah. Okay. So then what is my distance? The distance, again, I will copy this and paste it here. And I will remove these values. And distance is basically equal to, so the observed minus expected square divided by the expected. And that I calculate for each of them. So chi-square value is nothing but the sum of all these things. That's my chi-square value. Degrees of freedom is basically number of rows minus 1 by number of columns minus 1. So number of columns are 4. That minus 1 is 3. So it's equal to 3 into number of rows is 2. That minus 1 is 1. So 3 into 1. That is my degrees of freedom. What is the corresponding p value? P value is chi-square distribution right tail, because I'm trying to see that after that how much is this thing. And degrees of freedom is 3. And this is the value 0.05, which is higher than 0.05. So I can say that male and female are not significantly different. At least based on this observation, I cannot say that they are significantly different. They are, I have to reject, I cannot reject my null hypothesis. So although in normal eye, it is saying that they are different, actually other than this group, rest are more or less same. 8, 7, 15, 10, 14, 12 are more or less same. Only probably this group is where it is different, but that is a small part, not even, that is probably not impacting much to the overall thing. But if I reduce further, let's say if I make it 3, this will become different. So when it is 8, it is not coming. So this has some effect, but it's not coming up to be very big. That's how chi-square is done. In Python, it's one single line code, very easy to write. So first of all, you have to create a table like this. So create a contingency table. So is the first big job. So once I run, let me show how the table looks like. The table is basically this kind of 2 multiple arrays. Okay. So there, so this, you create this array, and then once you create these arrays, you put that in this chi2 contingency. It's again comes under spicy stats. So the same library we are keeping on using. Under that, chi-square contingency, and within bracket data. This is the function name, and I create the data set name. And I'm asking him to save these 4 things: the statistic, the chi-square statistic, the degrees of freedom value, the p value, and also the expected table. So this is the observed table. The expected table looks like this. And this is my chi-square value. This is my degrees of freedom. Corresponding p-value is this, and this p-value is saying that I cannot reject the null hypothesis. If this p-value were smaller than 0.05, I could have rejected the null hypothesis. So I will give you some data sets to play with to do certain hypothesis testing. We'll stop here right now. And the next session will start at 6:15. Saptarshi has been told to join at 6:15. We have one particular topic left. So let me stop the recording right now.